yeah, I spent a lot of my grad school learning and doing a lot of work with pair distribution functions. So we figured it'd be great for me to give you guys an introduction on this PDF method that's really useful for a lot of difficulties when powder diffraction can't quite cut it, either because of sample or because of what you're interested in. So spoilers. Okay, so what is the PDF technique? So I think we've heard a little snippets of it yesterday, but it's a total scattering technique that's used to determine local ordering. That's relying on the Fourier relationship between the momentum transfer or the scattering information that we get when we scatter photons through our collection of atoms, and then correlating that to what the real space information is of how those atoms organize together. So the way we're going to break this down is we're going to start off at the very end, which is what real space ordering looks like and how we want to break that down in a way that's meaningful for us to use. And then we're going to jump back in fully on the X-ray side, talk a little bit about how X-rays interact with matter, and which is going to give us some insights onto some tips and tricks that we need to do to actually prepare our data for PDFs. And then we'll start working our way into the actual PDF technique, and we'll start trying to bridge that Fourier relationship between what we get when we scatter X-rays and what real space atom correlations will look like. That'll help at least demystify a very big step, which is the Fourier transform. And then we'll get into actually what collection looks like in a bit more details, along with experimental considerations, and get into some of the cool things that we're doing here at Brockhouse to improve the PDF technique. So let's start off with something very simple as an atomic ordering. So we'll go 2D because it's a lot easier to look at than trying to visualize something 3D on a 2D screen. So we have atoms here arranged in a nicely periodic way. For those close up, you might see there's a little bit of weird random motion there. For people far away who don't have glasses, it may all just look like a perfect lattice. So if we're in the PXRD regime or the XRD regime, we could probably break this down quickly into a nice little unit cell and describe it fully. But let's, for the sake of argument, pretend that we don't know anything about Bronte lattices, or this isn't really crystalline, and we still want to find a way to describe it. Probably the easiest thing to do for us as scientists is, rather than trying to break something down to a 2D or 3D model, is reduce it into one dimension. So we can look at how atoms are spaced out with each other and radially from each other. So we can see, for example, for this atom, there's a couple atoms here that are 1 away, there's 2 that are 2 away, and there's some on the diagonals. And we could try to do that for every single atom in this box of atoms or in our big collection. And so that's what we're going to do. So we can start off with a single atom, and we can sort of draw a little circle around it with a certain radius and a slight thickness to it. And we can see in this area here, that circle isn't really touching anything, so there's no atoms there. But eventually, if we get to something like a distance of 1, and we have that circle over there, oh, we're touching 4 atoms. So if we're to plot a histogram of this, at a distance of 1, we've got 4 atoms there. And then we keep expanding out, and eventually we get to this side here, which is going to be square root 2 in this little model. And we see again now the circle's now touching 4 more atoms. We can kind of keep going out. Again, we're touching 4. And finally, in this last case, we're touching now 8, and we can see our histogram kind of continues. So we can kind of keep going out and repeating that out with a model. And then not only just doing this for a single atom, but we'd actually do it for every atom. So we repeat this with this atom, so on for our entire model. So I ended up actually expanding this into like 100,000 atoms. And with those random variations, I made tiny windows and did all that math for you. And we get something like this. So again, we start seeing that same form that we saw before. There's going to be some widths to these things due to all that random order that I tossed in there. And we can kind of see these 3 are the same when we get to that 4th peak where there's twice as much, and we see there's twice as much. And because it's a 2D model, you can kind of see this trend sort of has things increasing in a linear fashion, because as our circle gets bigger, it's going to increase by r. So if this were to be 3D and we're doing a sphere instead of a circle, this whole thing would be trending up by r squared. So this here is actually going to be called a radial distribution function, which is just another way of looking at a direct pair distribution function, which is just the first thing you get when you do a Fourier transform. But the important thing is that this sort of notion of interpreting an atomic model makes sense and is intuitive. We're working in real space. If we imagine there's some arbitrary atom here, we sort of get a nature of how many atoms and how their sharpness is as you go further away in spherical shells. So when we start trying to work on the X-ray side to get to this, we need to start thinking about how X-rays interact with matter. But before that, I'll slide a little bit into history. Joel already covered a couple of these things yesterday, such as were X-ray diffraction laws and the first powder diffraction measurements. But the idea of a PDF has actually been around for a while. So the first principal calculations that derived out the Fourier relationship between that scattering and real space density came out in 1927, so almost 100 years ago. And then it was about 3 years later where the very first paradistribution function measurement was done. From what I recall, I believe it was like on water. The amount of angle they went to was very narrow. The quality of that PDF was not great, but it was entirely a proof of concept. This is technically possible. And given that, we can see that the PDF technique pretty much sat on the shelf for a while. And it really wasn't until the 80s where we had the first synchrotron measurement of PDFs. This was a big deal at the time, and it took a lot of work to set up. Energy sensitive detectors were used, so there was a lot of lineup. And then for reasons that we'll get into later, collections would take a very long time to do because you're using point detectors and you're going over high angles. So this was a very cool technique, but there wasn't quite a good use case for it other than people who were very interested in specific structures. The big thing that changed, which I don't have here, is around the mid-90s. There was a big push from the US to start studying nanomaterials. And nanomaterials, it turns out, is a very good contender for the PDF method. And so with a lot of resources going there and a lot of people trying to do this, the big thing that happened was 2003, the first PDF measurement was done with an area detector. And this solved a lot of the time issues that happens with doing the old setup of a point detector. And so we went from data collection taking hours to seconds. And basically since then, the amount of PDF measurements that have been done have just shot up. Things have been getting faster and faster as synchrotrons get better and better and detectors are more and more efficient. And this has been probably the big revolution for why we're even here talking about PDFs right now. So getting back to X-rays interacting with matter. So X-rays are electromagnetic waves as well as photons. So they're going to like to interact with charged particles. And so we're going to start off with the electron. And while there's a bunch of ways we can interact, there's going to be two things I want to focus on. One is elastic scattering, which is that photon comes in, hits the electron, and then bounces off, still maintaining its same phase and wavelength. So this is the good coherent scattering that makes PXRD and all our X-ray diffraction possible. And then the other thing is Compton scattering. In Compton scattering, that photon still comes in, hits our electron, but some of that kinetic energy is imparted on that electron, so it moves a little bit, and that resulting wavelength is going to be at a longer wavelength. It's going to be not going to have any phase. It's going to be incoherent. It sucks. It's a reality that we have to live with, and we're going to have to address it, but it's not useful at all. So we don't want this. So from there, if we look at an atom is going to be a core, a nucleus core, and then taking up the vast majority of the space is the electron cloud. So atoms are going to be interacting with that electron cloud. And because those electrons are all in the little orbitals, we're going to start finding that there's preferred scattering that's going to happen. And that's going to be described by momentum transfer Q, which I've started mentioning early on here. So we have a little relationship here, which is going to be related to the scattering angle 2 theta, well, half of the scattering angle, as well as the wavelength of the photons being used. So atoms with more electrons are going to, one, scatter more, So this is where things like which is why we've seen heavier elements always scatter better than lighter elements, and things like hydrogen are practically invisible. And what that also means is that different ions, or if you still have the same charge, but you have different elements that have ions, you can still have sort of the same principal scattering power. But what we see is that as you go off of zero angle and you start going to higher scattering angles or higher momentum transfer, there's going to be a fall off here. And that fall off is dictated by the orbital structure of the atom of where those electrons lie. So this would be if we were to do a scattering measurement and we were to just, instead of having an actual material or a structure, we just scattered off of a single ion or atom. These would be the patterns that this would be like sort of the structure that we'd see. We just see this fall off and we'd have these weird curves that tell us a little bit about the orbital structure. So like all our powder XRD patterns and things like that, if you end up looking in log scale or something like that, you'll tend to see that it actually tends to follow the same sort of fall off in angle. And then from there, we can build up to when we have a collection of these atoms, we get to diffraction conditions, where when we get a plane of these atoms and we get a bunch of these coherent scattering conditions, we can get interference from different atomic planes, giving us constructive or destructive interference, giving rise to all our great diffraction laws and Miller indices. And then from there, those have always been based off of the assumption that we have relatively infinite lattice sizes relative to the photons that are coming in. But we probably went over this a little bit in Joel's talks about what happens when we start having smaller particle sizes and the broadening that we get. So as we get smaller and smaller, we start losing that infinite planes. We start getting something called diffuse scattering, where we start losing the sharp Bragg peaks and we get increasing broadening. And so as we get to smaller and smaller particles, or we get to something a little more amorphous, where we don't have any long-range ordering, we can still have very tiny, in some ways, planes described by like an atom-atom pair, right? If we look at things like liquids and stuff like that, where your basic laws of chemistry are still kind of holding, but there's just too much energy to whatever is happening to your material to have any of that nice, long, very pretty periodic ordering. But there's still information that's preserved here. So it's just a matter of trying to extract that out. So if we were to do this experimentally, the data collection process is actually fairly similar to what we would do in XRD with an area detector. So you have your detector here, you have your sample close by, X-rays go in transmission, it all scatters through, you get a nice little area pattern. We integrate that out. From there, we're going to do some factoring to remove some of the things that I talked about. So things like the atomic form factor, which is what everything kind of decays as. We need to remove any background scattering, background scattering, Compton scattering. And then eventually we end up with this interference function, which kind of looks like in Q, which is going to kind of, at least in this case with an amorphous example, kind of looks like a series of sine waves. And then it turns out if you Fourier transform that, you get the PDF. So this is a sine Fourier transform. So that interference function is basically this whole chunk together of Q, S of Q minus 1, where S of Q was that normalized to the atomic form factor squared. And we do the sine Fourier transform of that, and you get this real space contribution. Don't worry about memorizing these integrals or anything like that. Memorizing Q is always good. The amount of times you have to Google that quickly gets annoying. But with all these integrals, a lot of programs are just going to be ripping through that anyway. You're never going to be doing this by hand. And then from there, we can kind of reformat the pair distribution function, which is what we got directly from the Fourier transform, to something maybe slightly more intuitive, like the radial distribution function. So we just have the relationships here with this, where we define the subfunction little g of r. And we can see here, this is where we get that same increasing with r squared as we go to larger distances. And we start seeing these atomic histograms, just like we saw with that 2D example. So that Fourier, so basically the thing I glossed over is that little integral that really does all the magic for us. And I never became a big expert on Fourier, on really grasping that Fourier relationship, and I'm not sure how well versed everyone else is. But I figured we can go over some of the basics and at least build up a little toolbox to at least visually get a good sense of what's a semi-intuitive understanding of what we're seeing when we look at some of our 1D scattering data and how that can contribute to our PDF. So at least one of the big rules is when you have a sine function in reciprocal space and you Fourier transform that, you get a nice delta function. So if we have long periodic ordering in our XRD pattern, that's going to probably tell us that there's a very sharp peak somewhere. And conversely, if we have a very sharp peak, like a Bragg peak in our XRD pattern, that probably tells us there's very long range ordering in real space, which makes sense considering we have a periodic crystalline structure. So, but we only get a delta function when we integrate when that sine function goes out to infinity. In reality, we can't really go to infinity in momentum transfer. For starters, because of that sine relationship, there's only so high of an angle we can theoretically go. And from a practical standpoint, especially with 2D detectors, there's only so high of an angle you can go along with energy. So if we say terminate this if we make this box a certain length, what we see is when we now do the Fourier transform, we're getting these weird extra ripples here, which is called the sinc function. And for anyone here who's looked at PDFs or made a PDF before, I'm guessing these sort of ripples you've seen them before. So yeah, that comes from the fact that usually there's still signal that exists, but the window that we're integrating about is cut off before that signal actually dies off. So we can see as we go to higher and higher Q, these termination ripples get much smaller and smaller and smaller. But because in this example here, it's a permanent, perfect sine wave, they never really go away. The other thing we can look at is what the period is of our oscillations. So we can see as I change the period of the sine, we're seeing a correlated peak shift in our Fourier transform. And then the other thing is what happens as your signal dies down. So what we see here is, in addition, we see some of those termination ripples starting to go away, but we also see our peak here broadening out as it's decaying out on its own. So usually these things fall off. So one of the things is if you convolute in Fourier transforms a Gaussian into something, you'll get something on the other end. You'll get a Gaussian as well. So putting these tools together, we can start kind of building up a little bit of a picture of how these patterns come about. So let's try to maybe play around with a little bit of a toy example of perfectly fictitious structures that can never really exist in real life, but are simple enough that we can maybe actually try to have a little intuition as to what's going on. So in this case here, we're just going to start off. I made up a little RDF that just happens to have a single Gaussian peak at 4, but no other structure beyond that. So while this isn't physically possible, we can take that RDF, convert that into a PDF using those equations I showed before, and then just doing that Fourier transform back. And sort of like I mentioned earlier, going over those rules, what we're seeing is a Fourier transform. We're seeing a sine function that's decaying out due to that width of the Gaussian. We can add another peak to this and convert it again. And again, now what we're seeing here is we're seeing something a little weird here. We're seeing a little bit of beating on this pattern because these two are kind of spaced off by a factor of 2. So there's now 2 sine waves of 2 different periods by a factor of 2 overlapping on each other. So we're getting a little bit, and because of their different intensities, we're getting a little bit of destructive and constructive interference over them. So we get this nice little beating pattern that still dies out. And we can add a third peak just for fun to make things look a lot more complicated. I threw it over at 7 to just absolutely make it not coalesce nicely with anything else that we have here. And now when we do this, we start getting even weirder structures here. So you can start imagining as you get something even amorphous in structure that might have a few peaks, you can actually pull out a very complicated looking scattering data from it. And then conversely, if we were to actually have like very long ordering over here, we might actually see some sharper peaks show up in our fake scattering data. So let's try to work through a more realistic example. So this here is nickel that was collected. The contrast here isn't great, even me looking at it from right here, so hopefully, but over here there's a little bit of a beam stop shadow, and we can see some rings and they start dying out pretty fast, but you can trust me, there's a lot of rings going out pretty far into this pattern. So the first thing we're going to do is integrate it out. And I have this here in log scale because it's usually the best way to sort of see how your pattern actually scales with the atomic form factor. So we have all these little peaks, and we can actually see our peaks go down pretty far, and then probably about after 20, it looks like things die down a fair bit. So this atomic form factor squared, because it's just nickel, it's just going to be the atomic form factor of nickel. But if you had any other material, you would combine and ratio all those elements that you have in there. So for anyone who's made PDFs and GSAS already, that's usually the reason why you get that pop-up that yells at you to list all your elements when you're generating your PDF, for anyone who's happened to try it. So once I normalize that atomic form factor, we see our intensities have dropped a bit, and we see, at least at high Q, everything seems to normalize at about 1. So that was that S of Q. And then from there, we're going to do that renormalizing to F of Q. And now here's the interesting thing is because this gets multiplied by Q, as you go to higher and higher Q, your signal that exists there gets amplified. So I'm going to hop on the side. That stuff over here, after 20, that I said looked like it died down, looks a lot sharper. And it looks like here, just at the very end, is where we start seeing a little bit of noise for the people who are close by. But even here, you can actually still make out there's a lot of peak structure here. And then we can do that integral of the sine Fourier transform. And we get this little slope here at the beginning. And we can see we have a lot of peaks that are going on here. And especially when you're looking at a very large range of R, this can look a little bit intimidating. And usually you'll probably just want to focus on sort of the regions or distances that you're more interested in, or looking at how far out the signal goes before it dies down. But one thing I want to point out is that, so this negative slope over here actually has some information to it. It's actually going to be related to the number density of your material. So you can actually rescale by this fact based on the slope, and you can convert it into a radial distribution function. And we see we get it. At least over here, we go back to that nice histogram that matches somewhat close to, that follows that same pattern that we saw in the very beginning. So in terms of applications, like I mentioned, we can use things to characterize nanoparticles and nanoparticle size. We can also use it for peak identification and elemental bonding for structure analysis. So for a lot of these elements, we know what the bond lengths are for certain elements. So in this case here, we have a calcium fluoride matrix, and we can actually map out, okay, this here is the calcium fluoride, fluoride, and second nearest peaks within this unit cell. And we can actually go on to solve structures and model structures using big box or small box models, which Graham's going to be talking about in more detail in the next talk. So I'll leave that for him. And similarly, we can also look for evidence of certain bonds that may or may not be happening. So this example here is a single atom catalyst, where we're trying to see if nickel was actually like dispersed fully within this material, or if we were getting nickel clusters forming. So in this case, we can take the PDF of this cluster of this catalyst with nickel in there and compare it to just nickel-nickel where we know what that nickel-nickel bond is. And following that out, we can actually see there is no bond there, and we can characterize all the other bonds. So we can actually pull out a lot of information there in solving specific problems. So this all sounds really great, and I'm sure everyone here is very excited to do PDFs, and maybe for some people it sounds too good to be true and too easy. There are a lot, because the measurement process is a lot, because the measurement and the Fourier transform seems simple. Simple doesn't necessarily mean easy. Usually the more straightforward something is, the more ways there are for things to go wrong. And so now we need to get into all the things that can result in a bad PDF. So this is going to be dealing with the fact that detectors aren't perfect. And that when we do a measurement, there's concessions we have to make in terms of accessing high Q or momentum transfer, as well as even the resolution of the scattering data that we collect. Sample quality is always also going to play a role. We're going to circle back, talk about some Compton scattering, as well as all the non-sample scattering that I haven't mentioned yet. So with momentum transfer, so in addition to just termination ripples, the other thing that can happen is that as we don't go far enough in those oscillations in momentum transfer, we don't get a good sense of how sharp those peaks are. So by doing so, we end up introducing our own sense of broadening. So even here on this amorphous sample, as we reduce and introduce a convolution here, where I just go out and just effectively reduce how far out into Q we were to do a Fourier transform for, even in something amorphous, you can start seeing the ability to resolve two peaks, even if they're naturally broad, gets even worse. So the simple solution is, well, we know Q is related to our wavelength and angle. Why don't we just get that detector as physically close as possible and get an energy as high as possible and just make Q as big as we possibly can. And we do that to an extent, but there's also some trade-offs here. So in this case here, I just vary sample detector distance. It'll be similar in some ways to varying energy. And what we can see here is that just by pulling our distance, we can get more signal. But what we start seeing is that in our transform, and I'll just get a little zoom in here, we start off in our nearest neighbor peaks. Going out further benefits us really nicely. We get sharper nearest neighbor peaks. But as we get further out in the distance, especially towards this end, we start seeing a point where they match up. And then now suddenly our longer detector distance, where we had better Q resolution, starts getting us sharper long range peaks, because by our detector pixel resolution being better, we're able to better capture the sharpness of some of those Bragg peaks in crystalline materials. And when we do that, that means we're more accurately capturing the long range order of the material. Whereas by going further out into Q, we can better capture the short range ordering. So there's a little bit of a trade-off here. And ideally, the best solution would be impossibly tiny pixels going to a very high angle, but then we play out with the trade-off of time measurements, right? We can go back to what we did in the 80s, but I don't know how many people are very keen on spending half a day taking a measurement. And we can kind of see over here too, just if we were to change energies, if we were to keep the sample detector distance the same, we could get, for the same angle, we can get slightly higher Q. But because your pixel is a finite size in a detector, the angular spread is going to be constant. And so if your relationship to momentum transfer in angle is going to change depending on your energy, you're capturing more Q in a single pixel, which can be troublesome for very sharp peaks. So the other thing is Compton scattering. Said I would come back to it, and now's the time. So Compton scattering is particularly annoying because while our atomic form factor falls off at higher angles, Compton scattering likes to do the opposite, and it goes up at higher angles. It's particularly a much bigger problem in lower Z materials. And as you work in higher energies too, with lower Z materials, it gets worse and worse. So it's something you have to take into consideration. The nice thing is that because Compton scattering doesn't really have a structure to it, so if you know what materials are in it and the energy you're working in, you can correct with it and presume it using software and try to subtract it out that way. So at least on your practical end, it's not something you really have to worry about directly, but it is something to be aware of. And then the other thing is background scattering. So there's a lot of things that, because now we're taking the Fourier transform of everything, there's a lot of things now that we can't ignore, like what we do with powder diffraction, where Joel can go and in GSASS do that nice little background fit with like the Chebyshev or point fit, and you just remove it all because a lot of that stuff is signal. And we have to figure out what part of that is actually signal that we want to put in our Fourier transform and run through the PDF method, and what stuff is junk that we actually doesn't belong there. So in this case here, from that same nickel measurement, this is just an empty Kapton capillary. And we can see now, especially when there's no big bright rings to capture things, there's a lot of weird things here, right? There's still some scattering here. You can kind of see this faint like intensity here that whooshes out. There's some weird tails here for those who are close by. So those are weird artifacts that definitely aren't our signal from our nickel or any other material. So we need to make sure that we actually capture these so that way we can subtract them out from our data. So the important thing here to remember is that getting background measurements is absolutely critical. And so with that, here are all the pro tips for anyone who wants to do PDF measurements. So probably for you guys to ask yourselves coming into experiment is, what are you hoping to actually solve with your measurements? Are you interested in short range ordering, medium range ordering? Are you looking at it, you just want to see how something's changing comparatively? Or are you planning to do some modeling and trying to get something more quantitative? Knowing these and bringing it up with your beamline scientists, that helps us prioritize certain things. If you are interested in short range ordering and you want really good short range ordering, then it makes sense to, let's bring everything nice and tight, get that energy high possibly, and let's get as good as we can of that high Q. Conversely, if you're interested in medium range ordering, maybe it's not worth those concessions. Or if you're doing something in situ, going very high energy might not be worth the loss in flux. So knowing that ahead of time lets us make sure that we can kind of set up the best possible scenario for you guys. The other thing that's helpful for you guys to know is if you have if your sample possibly has low angle scattering. So this would be usually if you have any large crystal lattices in structures like that. I think Bob even mentioned in one of those really long powder diffraction unit cells where even there in powder diffraction, one of the peaks got captured by the beam stop. When we shrink everything down in size and make everything tight, especially with higher energies, that's very likely to happen. And losing a peak when you're trying to do a Fourier transform can be very bad. So knowing that in advance means that we can, especially if you know roughly where that is in angle or Q, means that we can try to set things up to make sure we actually capture that data and not lose it. And then from there, this is stuff that your beamline scientist is going to know and will answer for you on your experiment. But being aware of experimental parameters, so checking in on what the choice of energy is and whether that makes sense for your experiments based off of what you want in Q or flux, like I mentioned before. Also being aware of what detectors being used. Detectors aren't perfect, and every detector has their own quirk. And because we work with our detectors every day, we know the quirks really well. And it's going to be helpful for you guys to probably be aware of some of those things. So important things that you should know are pixel size. And then in terms of quirks, things like, does your detector have afterglow? So a lot of medical detectors, medical X-ray area detectors, which are very popular in synchrotrons for these because they're thin and they're cheap, relatively cheap, are very handy. But if you blast something with really high intensity, especially to buy share rings. Some of those rings can kind of still linger for a bit before they die out. And that's very helpful to know about, especially when it comes to taking background measurements. The last thing you want to do is superimpose something else. The other thing is dark current. So if there's no X-rays hitting it, does it have a signal to it? And make sure and being aware that that's being removed. And then the other thing is your detector actually responding the way it should? So does every pixel, when you hit it with 10 photons, actually counts something proportional to 10, or does it vary depending on where you're hitting it on the detector? And then probably the very important thing that you should know, and your beamline scientists will probably always hammer it in, because is the saturation level. So how high of a count is going to be the maximum count that the detector can allow? Because usually when you go above that, you could be damaging the detector, and also if you're hitting that saturation level, you're not getting anything useful out of it anymore because you don't know if you're hitting a maximum. But these are all things that we would tell you, and usually we'll tell you like, yeah, don't go above 80% of 65,000, or like, which is 16 bits. And then usually something that's always handy to know is what your beam size is. And then also finally for you guys, collecting more background images than you think you need. It's annoying, it's not interesting because it's not sample, and usually everyone has a lot of samples. But one of the worst things that can happen is not having a background for something when you need it. And it's happened before, and because of the nature of these setups, going back and reproducing something can be very difficult. We had a user once doing a battery PDF measurement. They forgot to do a subtractive background of their empty battery. So we did our best to try to reproduce it, but it's not perfect. And it wouldn't have been as good as just capturing it on the experiment when everything's set up. And then finally, keep it simple. Because every little setup change is going to probably change some of your backgrounds and things like that. Finding a good middle ground for all these things is probably your best course of action. So if you're looking at a lot of things, we're interested in long range ordering, short range ordering. If you're really focused on something, you can change up your experimental parameters, but the easiest thing might be getting one good setup where everything's consistent and you're going to get consistently good data, and you'll have a ton of backgrounds, you'll have a ton of data. You can really check if something's weird with your sample or something was weird with the setup, and you'll know that ahead of time, rather than going through a setup change on every sample. So looks like I got about a bit of time, so we'll get into some of the things we're doing at Brockhouse. So at least at our high energy beamline, we can go from 20 to 95 keV. So we also do rapid powder XRD. And from there, we can also do in situ measurements. We can do high pressure. We have furnace cells and cold air streams, so we can do different temperatures. And in addition, we can go to higher energies and do a lot of the same things with PDFs. So doing things like temperature sensitive PDFs as you're heating and cooling something down, or getting very low temperature stuff. And similarly, if you have some device, usually we can try to accommodate that as well. And then finally, at least one of the new things we're trying to do is trying to improve that data collection process. So I mentioned a lot with this sort of direct and typical process where we have the detector centered on our beam and we collect these nice little beautiful rings, just like what we do in powder XRD. And while it's great because we can azimuthally average over every single ring and get really good statistics really fast, if our goal is to try to collect high Q, we're kind of shooting ourselves in the foot because we're only really collecting half, we're only really using half the detector. So one thing we could do is we can try to shift the detector up. And when we do that now, suddenly the highest angle we can get at a given distance is a bit higher. And we actually did that for a group last year because, yeah, they had something with very low Q structure that they wanted to capture. And they were also doing stuff in situ where they needed data collection fast. So they needed low energy, low Q, but also high Q for PDF. So we actually raised the detector up to the bottom edge and collected that, and actually worked out really well. But then we can think to ourselves, what if we take it a step further? What if we tilt the detector So that way we still have that same distance, but now rather than just collecting like some angle here, we can actually collect all the way out to 90 degrees. And it turns out doing that actually comes with a lot of advantages. So besides the obvious that by going to higher angles, we get higher momentum transfer, it turns out that by tilting our detector, suddenly all those pixels that you have are, especially at low angles, at low scattering angles, are going to be also at an angle, which means the amount of area that they can access, and so their angular acceptance gets a lot lower, which means you're almost for free, you're actually getting some of the benefits of a large sample detector distance at low angles. And then as you get to higher angles, that angular acceptance goes down, but usually there is where your signal gets weak and you actually want to get as much signal as possible. So you find yourselves actually getting the best of both worlds. It also lets us be able to use lower energy X-rays, so we can get much higher flux. Depending on your material, you can reduce Compton scattering and still get an equivalent PDF that you would in traditional geometry at high energies. But this becomes a lot harder. Getting the geometry just right, especially when you're dealing with high angles, becomes a lot harder. The slightest variation becomes much more sensitive. And especially when your signal gets weak, it's very easy for something to slip in there. The other thing is that since our atomic form factor falls off, our signal at high Q gets incredibly weak, which means any little bit of noise that's happening here can easily pollute your sample. So now all those little background measurements and things that I mentioned before, they're not just important, they're absolutely critical to get the best and useful PDF. And the moment those are bad, you're throwing away all that data that you worked so hard to calibrate your detector for. So you need to do more frequent background measurements as a result. The other thing is we give up the ability to fully average over those rings. So you may need to count longer if you're working at an equivalent energy. And it also means we're going to be more sensitive to graininess on your sample. The good news there is there's ways to mitigate that, such as we can jiggle the sample, so moving it in and out, or spin the sample to help average out any errant grains that are in the beam. But the result is when we compare it is night and day. We get something much sharper. Those termination ripples that exist, that seem to always exist, are even smaller now. We kind of have to really zoom in, and even in the inset here, you can barely see those ripples. But you get something incredibly sharp. It just takes a lot more computational work to get it, which is actually some of the work that we're doing on implementing that on the c.l.s end. So that way you as a user, hopefully when beam time returns, can come with a sample and you can basically walk out with a PDF like this, just using the computational power and software that we're working on over here. And when you get things that quantitatively well, you can even start doing things like we're finding out structures like these rubidium chloride nanoparticles, and actually get into more quantitative modeling. We've even done stuff like pulling out nanoparticles from a graphite substrate, and then actually comparing different nanoparticles. I don't have figures of that because that was one of the last measurements we took before the beam dump. So we're still processing that and interpreting it. But there's a lot of power behind this once you can get over the hump of the setup and computational work. It's almost the perfect compromise between those 12-hour measurements that happened in the 80s and the quick 1-second measurements that we can kind of do now. So to sum up, the PDF is a very useful tool, especially when we want to probe local order and structure. And we can see there's information on local ordering regardless of whether we have crystallinity or not. It's either going to show up as a lot of Bragg peaks, or we're going to see some form of long-range oscillation throughout your pattern. This is a method that is fairly critical for synchrotrons due to that higher energy you need just to even theoretically access higher angles, which is great for us as synchrotron. And in terms of software, working with GSAS is probably your best de facto tool to use. And It's very simple to do in GSAS. It's in some ways almost too easy. It's pretty much a few button clicks to get yourself to a PDF. But I have the math here that goes into everything that we did. And while it's not, I wouldn't call it trivial, it's something that even with a little bit of coding background, someone can do them, you can do yourself. And I would say, as my advice is, if you are interested in PDFs and understanding them, I wouldn't use it to publish your own data necessarily right off the bat. It's a fun exercise to try to follow along with your own code to make a PDF. And the nice thing about it going through step by step is similar like how we went through in this presentation, you can start taking away little subtleties of what steps are doing what. And that's pretty much how you learn about this. That's pretty much how I learned about PDFs, was just trying to reproduce it on my own. And you start learning about what steps are really happening everywhere. So I just want to give a shout out to our Brockhouse team. So I think most of these faces you've seen already. I guess the only ones are Phasia, who will be giving a talk tomorrow. And then there's Stefan Kitcha, who's our Beam team leader of Brockhouse. And his team actually led the tilted geometry PDF work. I have our contact info here, as well as our Brockhouse website. And yeah, I think all these talks are going to end up on our Brockhouse website. So you can always check this out and see these slides there. And I just have some resources here in case you want to do any extra reading. So thank you.
Questions?
Question.
There are no dumb questions.
That's good. Can you make a PDF out of any XRD pattern?
So any powder XRD or like
Powder XRD.
So technically, yes. The thing is if you remember, here we go. So remember that max Q. So if you're looking at, say, so most cases, like I think our XRD, our high resolution powder XRD that we do at our low energy wiggler, I believe it goes out to roughly 9 inverse angstroms. So you can kind of see here that that convolution that you get gets really bad. So it'd be similar to sort of the very first PDFs that you do, where the amount of noise that you get just from terminating out and losing a lot of your higher signal would just wash out a lot of things. You might be able to pull out something basic, but
I just wanted for
fun.
Identification, for example, I had two amorphous materials. I just wanted to compare them.
They would have to be very different because of just the broadening that you would get from, and then also you would need a background subtraction as well if you manage to collect those when you're XRD measurements. I would say it's worth a try, but it's very unlikely that you would get something useful. Usually, I would say 20 inverse angstroms is about the minimum I would go for a PDF if you wanted to just work off of that. I've seen a couple at 15, but especially if you're looking at something where comparing things where ordering is close, like within an angstrom of each other, a lot of that can get washed out, and you might not get anything meaningful from it.
It take you 3 minutes to compare
Yeah.
PXRD to PDF and GSAS, and you can.
Yeah, I would say if you want, you can always try. Yeah.
Give it a shot.
I could add something to that too. So as far as doing PDF on like a lab diffractometer, use like a copper tube. Your Qmax is going to be on 8, which is just too short. Your peaks will be super broad. You don't have anything. People do it sometimes using a molybdenum and silver tube. Like molybdenum, you can get a low resolution PDF. In silver, you can get like a reasonable PDF. But the flux for those lower, like go to molybdenum, the flux drops, and silver, the flux drops a lot. So you can do very like basic ID PDFs on a lab machine, though you're going to probably need to count for a couple hours for like a whole day to get, reasonable statistics. But people do it.
We take PDF measurements off a silver tube on our lab instrument, and we count for about 48 hours
Yeah.
to get even reasonable amounts of noise.
Yeah, there's also one other subtlety I want to add to that, which is because of that background subtraction that you need to do, the worst thing that can happen is if you end up in a situation where you have 0 counts. Because then that means you're missing, because your signal should be falling off with the atomic form factor. So there should still be a little bit of counts there. So usually what you need to count enough to get some signal there. I think usually on lab setups, you probably count to you have a variable count time, so you probably count to signal. So you're not wasting a ton of time up here, but you need to make sure even after your background subtraction, you still are left with something over here that still normalizes. If it falls off, then you're not going to be able to use that.
Yes. Scott.
I have a dumb question too. So in the since those ripples are a function of your limited ability to scan to super high Q,
Yeah.
Those why wouldn't you just mathematically sort of subtract that out of the data because you know what you scan, the Q you scan to, and then why don't we leave it?
So it's due to the finite nature. So the only way to really get around it is to know what your signal is beyond that window, right? The window is determined by the fact that you haven't measured out beyond that threshold. What people do is they'll add a damp factor. So yeah, GSS has this capability as well, where they introduce an artificial damp that'll bring the signal at your max Q to 0. But what that does is it introduces rather than having your termination ripples, it introduces a broadening. So people do it, but you're just replacing one artifact with another. So personally, I'm not a big fan of damping.
Thank you.
Yep.
Yeah, hi, thank you for the presentation. Could be a dumb question. I'm just wondering what's the highest resolution or the smallest feature sets you can observe in the short range structure. Say I have an inorganic metallic sample, there's some elemental distribution. I've seen people do PDF through atomic probe tomography, APT, to see really those one atom and say some of its neighbors. Would that be something we can do in the BXDS slide? Yeah, it could be say it's an alloy, different elements, and in some regions there are some elements tend to cluster into each other. I don't know the exact size, could be tens of nanometers or maybe hundreds. Would that be something detectable?
It's possible. So there's a few things. One is going to be our instrument capabilities, and especially if you're trying to do something depending on speed versus getting really good counts. The other thing is temperature. So if your sample is warm or room temperature, or if your distributions are broad enough that they practically overlap, then no matter how well you measure, right? If you're theoretically they overlap perfectly, and you can't deconvolute that on a theoretical model, you're probably not going to see it experimentally. So often, especially with these tilted geometry measurements where we go to high Q, we'll usually use our cold finger and reduce the temperature down to 80 Kelvin, because when you reduce that thermal noise, the long range atomic ordering gets sharper and sharper. And you can actually, and those nearest neighbor distances are going to coalesce tighter together. So you can pull out sharper peaks because it doesn't have thermal noise in it.
Nice talk.
Thanks.
First question is, do we have the access to the slides? There's stuff.
Yeah. After the session, they're gonna end up on our website.
And one question is, how do we judge that the peak is the peak, not the noise? How do we make the judgment?
Like in a RDF or in your scattering in your PDF. So Oh. Okay, we'll just have a look at the end. Just pause the things. Okay, so odds are in terms of peaks. So, so you're thinking of mixing up this as a peak, basically. So with termination ripples, one is that they're going to be symmetric and they're going to follow this form of a sinc function. So you can actually, if you are worried that maybe there's like a tiny peak that's also buried in there, you can probably try to actually fit a sinc function to your primary peak and then compare out. If you're looking for something very subtle that might be buried within a sinc function. The other area where there could be noise, we go to, is usually way out in very early R, which is usually where usually a lot of residual noise that didn't get removed from your background usually ends up living when you do your transform. Is there's a lot of random noise and oscillations that can happen here. The cleaner this is, usually the better of a job you kind of did prepping your data, but this will rarely ever be perfect. And even here, it's not absolutely perfect. There's like a weird little dip here. But usually the stuff that exists before your stuff could look like a peak, but you can kind of, at that point, you probably use just bond lengths to kind of tell you whether or not it makes sense. And a lot of this stuff usually lives below 1 angstrom. So it's pretty apparent it's not real.
And also at the higher R revision, we can like peaks. So
well, at least in this case, there is still stuff here. Yeah, I don't have a slide here where I go out really high. But probably a good example here is just in QC, you'll see something a little analogous here where things just look really, where these things start getting noisy. You'll start seeing things like that at very high R, where the noise, the statistical noise, will also start playing a factor, and lines almost start looking thicker as a result of that.
okay, and one more question is, like imagine like we have two different atoms with different electronegativities.
Yeah.
So do we find the difference in the feeds in the PDF? Like they have different electronegativities, like the intensities or how do
Yes. Yeah, sorry. This is actually one thing I did forget to mention, which is a very good question. So, if you remember, electrons like to scatter off of electrons, and the scattering power was related to that atomic form factor, which is Z, and the whole thing's normalized with Z squared. So, the strength of these peaks are going to be related to the Z of the principal atom and the secondary atom. So if you're looking at nickel-nickel, it'll be, I forget the number of electrons in nickel. If anyone knows that, it's going to be that squared versus nickel hydrogen or something like that. So yeah, heavier elements, especially heavier elements together, are going to scatter much more strongly than weaker ones. So one of the big challenges is if you have a lot of very heavy elements and you're interested in something that's happening with light elements, a lot of those light elements will be practically invisible just because of the scattering power of everything else is going to completely dominate it. That's actually a very good question.
Can you say again what this negative slope here is a function of? And then also my second question is, what's the implication of negative intensities for some of the data?
Oh, so the idea of this is that this whole thing, if you were to integrate out this whole PDF, it should sum up to 0. So that's where that dip comes in. So if we, so yeah, this is sort of like the spherical particle baseline. You have all these peaks that sort of add up. And then that's also similarly why there's sort of this little F of Q preparation here, where this whole thing also needs to add up to 0. And in GSATs in the process, there is like some scaling stuff there to help make sure it is there, because that'll lead to a weird Fourier transform.
one last question?
Absolutely.
So can we do the PDF for samples like proteins?
You can. Yeah, you can. It's gonna be very hard because it's organic.
Yeah.
So there's gonna be a lot of Compton scattering. It's protein, so there's a lot of low Q scattering, especially if it's in a crystalline structure. And there's also radiation damage that can happen. So I would say with something like that, if it's prepped, there would have to be a use case. Unless you think there's maybe something amorphous in there.
At low angle. At very low.
It would be very difficult. I think in terms of solving that out, we might get a sense when Graham talks about modeling and solving structures through PDFs, where a protein might be pretty difficult to do. I don't want to say it's impossible.
Yeah, I think because you're gonna have all these different bond lengths that are basically the same.
Yeah,
You're gonna see like, you have lots of carbon-carbon bonds and carbon-nitrogen bonds, but you're not gonna do so much.
yeah, you'd probably need to see something. I would say it may even be possible that what may look like an amorphous hump could actually be a lot of rag peaks that are just kind of almost stacked on each other and just almost creating this like illusion of an amorphous peak. And it may mean that you just need slightly higher resolution Bragg scattering to resolve that out. Yeah, for something like that, I think all the compromises of PDF might end up hurting your might hurt your measurement more than it would help.
Any more questions? But if not, please help me greeting the speaker again.